Good evening, all. Well, all three.
Morning, Professor.
Morning. Well, time differences, they're such a pain. Good. We'll wait 2 more minutes or so and I will see. I've had one question so far, so I'll start by that. Oh, that's linear regression. Okay. I'll start with the question from this chapter and then I'll move to the other question afterwards. It doesn't seem a lot of people are joining, so we'll do it like this. So the question was on this slide where we have the model selection. And then I said, choose which model is best suited for the goal and base this on goodness of fit and model complexity. So you have a trade-off. Goodness of fit will fit your data points in your training set very well. But the model will then become more complex. So there will be more fluctuations, there will be more parameters. And then at a certain moment, I mentioned that the accuracy thus would be less. The accuracy of the parameter estimations would be less. So the accuracy that I mean there is really the accuracy on the parameter estimation. So if you have, so if your model is complex, this means that you have a model with more parameters. So the more complex your model will be, the more parameters or higher order parameters will be in this model. But you have just one data set, so you have a fixed data set in this case. Your training set. And let's just say this has n observations. In a very simple, whatever, my S is falling off the slide for me, so it's n observations. But in a very simple model, you will have very few parameters to estimate. And then each of those estimates will be very accurate or can be very accurate. So you will get an estimate for parameter theta 1, for example. And an accurate estimate here will mean that it has a small confidence interval for this parameter. Theta 2 with also a small confidence interval. If this is everything in parameters, other way, it's easy. If I have a more complex model, then I would have theta 1, theta 2, up to, for example, theta 10, which I have to estimate. But my data set is still the same, it doesn't increase. So I just have a limited amount of information available to do the estimation of more parameters. So here I will get estimates as well for the parameters, but the confidence intervals, they will be bigger. Just because I cannot estimate it as accurately as I can do with less parameters. So that's what I meant with it. The accuracy that I talk about is the accuracy of the parameter estimation, not the accuracy of the model. If that explains or clarifies. Okay, good. Then the other question was on linear regression. For backward selection, is it correct that we remove the least significant terms from the full model? Yes, because those will have the least influence on the model. So if you do a forward, you start with nothing and you add the one that is most significant, so that will have the biggest contribution. If you start with a full model, you move backwards, you take the ones out which have the least contribution, so you keep the ones with most contribution. So yeah, backward you remove least significant one, forward you add the most significant one. Any other questions? The part in chapter 10 was mostly introduction, so next week you'll get a true parameter estimation. And then we move.
Can I ask for previous chapters?
You can try, and I will try to answer.
Okay. I actually have problem on understanding the principal components. So in the slide, there are execution of principal components in R, and the outcome is standard deviation and rotation. And for rotation, I cannot understand what does it mean.
It's just a naming. So I'll answer you, Drew, first, because it's a quick question, and I'll move to the slides on principal components.
Okay.
So is it okay to say that homoscedasticity assumption is valid when the plot has a certain trend? Yes. So normally you will clearly see that if there is a trend, that the homoscedasticity will be violated. So if you see that the width is increasing, or if there is an upward or downward trend or whatever, then homoscedasticity will normally be violated. And then principal components. Let's see. Do you have the number on the slide?
15.
Yeah. No, this one. Yeah, rotation doesn't matter. It's just the naming. What is important is that you have in this table, this gives you the principal components. So this is just the naming that R gives to it. It calls it the rotation matrix. I also don't know exactly where the name is coming from, but the important thing in the output is that you have here the principal components. If you look in the columns, so the principal component in the first column, principal component in the second column, and the third one in the third column.
So then just there is no data reduction, right? 3 to 3.
No. Your principal component analysis does not do data reduction in itself. It will just calculate all the principal components, and then the user will choose how many to use based on the standard deviations, because you know that the variance is equal to lambda, so you have to square this and then see at the proportions how many that you keep. But the principal component always gives again n principal components, and then the user chooses how many of those he will keep.
So the next slide is how to use these values for principal components.
Yeah, so this one is lambda 1 divided by lambda 1 plus lambda 2 plus lambda 3. So the lambdas you get by squaring the standard deviations. The second one is lambda 1 plus lambda 2 divided by all three, and then this is everything. And then you can see this is 96%, this is 98%, with 2 principal components, and of course 3 principal components explains 100%. So in this case, already with 1 principal component, you explain 96%. So you could reduce from 3 to 1 variable.
I see. Clear.
Okay.
Thank you.
No problem. Any other questions?
Not for me, at least,
Okay.
because I even touched the next chapter yet. Sorry.
It's okay. The advantage is that you have the video, so you can do it on your own
Yeah.
pace. But
I already gaining some advantage from it. Thank you.
well, if there are no other questions, then I'll see you next week normally, I think. Let's see. So this week was 10. Yeah, so next week, the second part of chapter 10. Next week we have 2 theory classes even. So yeah.
I just have a question.
Yeah, okay, right, wait, you also send me one. There were questions related to observational score and biplot. Since we did not learn these topics during the lecture, should we? No, you don't have to study the theories regarding this. You just will be able or have to use it if necessary, or be able to use it. But if you did not get the theory about it, it's well, you don't have to look it up or learn the theory of those things. And then Seungchang.
Yeah. For previous, for latest project, who gave the score? Who measured the score?
Negin does the score and I review.
Okay. So if I want feedback for that,
if you want feedback, you can just make an appointment with me.
Okay. Okay. Thank you. I will email later.
Okay, perfect. So if there are no other questions, then yeah, we'll have to see. I'll have to see how I do it with the Q&A next week, because we have theory on Tuesday and Thursday. So I'll probably do not put one next week, but the week after, in the beginning of the week, so we can do both classes at the same moment. But I will announce everything to you, Flora, and then we'll see how to continue. Okay. Thank you for joining. Have a nice evening. And then I will see you next week, or in 2 weeks, or whenever the next session will be. See ya. Bye.
Thank you.
Thank you.